Hello, class. So on this video, we're going to start on section 3.5 in the book. Right? So in the previous videos, we finished sections 3.1, 3.3, and 3.4. So now, again, we're on section 3.5 in the book. So what is section 3.5 about? So I mentioned this in the previous video. What have we done so far? Well, as of now, we know how to find the general solution for any second order homogeneous ODE with constant coefficients. So what happens if we want to make that more general? Specifically, what happens if we want to find the general solution for a second order linear ODE with constant coefficients that is not necessarily homogeneous. So that's equal to g of x, where g of x is not necessarily equal to 0. So g of x could be equal to 0, in which case we know how to find the general solution. But what happens if g of x is not equal to 0? It's just a function of x. So an expression involving the x variable and constants. Is there a way for us to generalize the solution method that we found in the previous sections for the homogeneous case and extend it to this general differential equation where it's not necessarily homogeneous? Well, it turns out that there is a way to do it, and it's going to be pretty easy to use. First, I need to give you a definition, which I already wrote down here. So let me label this differential equation as star. Let's see what the definition is. So any solution of star, and star being this non-homogeneous. So in fact, okay, so this definition works in either case. So any solution of star that doesn't have arbitrary constants, right? So a solution y of x, that's a specific solution, right? So a solution that doesn't have any arbitrary constants in there, just y of x equals some expression involving only x and specific constants, right? So like y of x equals x squared, y of x equals sine x plus 3, a specific solution without any arbitrary constants, right? So any solution of star that satisfies this, right, it is a specific solution. We're going to give it a name. We're going to call it a particular solution, and we're going to denote it by y sub p. Y because it's a solution, right? The variable y because it is a solution, and subscript p because it's a particular solution. Right? Now, this is all the setup we need. Now we can go directly to the theorem. I'm just going to write something here. I'm going to make it specific that g of x is not equal to 0. Okay. So this is the theorem that we're going to use to solve differential equations when they're not homogeneous. So suppose that y sub p is a particular solution to star, to the non-homogeneous differential equation, second order linear non-homogeneous with constant coefficients. And suppose that this particular solution has interval of definition I. Okay. Now, furthermore, suppose that y of x is the general solution for the associated homogeneous ODE, right? Meaning that replace g of x with 0, find the general solution for that, and label that y of x. And suppose that this is the general solution on the same interval I, right? So we have to find a common interval of definition for the particular one and the general solution to the homogeneous case. That is all the setup we need. Then the general solution for the original ODE, the non-homogeneous one, is given by the sum of the general solution for the homogeneous case plus the particular solution that we found for the original ODE. And this is the general solution on the interval of definition I that we found before, right? The interval of definition for which the particular solution and the general solution for the homogeneous ODE, right, in which those work, right? So the shared interval of definition. So what is this theorem telling us? It's giving us a way to find the general solution for the non-homogeneous case. So what is it that we need to do? And I'm going to say it in this order because this is the order in which we're going to do it, in the examples. First, what we want to do is we want to find the general solution for the homogeneous case, right? So replace g of x with 0, find the general solution for that. We know how to do that easily because of the previous sections. Okay? So label that general solution y of x, and we know that works for all real numbers. After you have that, find a particular solution for the original non-homogeneous ODE, right? So a solution that doesn't have any arbitrary constants. It is a specific solution. Once you found that particular solution, and it has its interval of definition, the general solution for the non-homogeneous ODE is just going to be the sum of y of x, which is the general solution for the homogeneous case, and y sub p, which is the particular solution for the original ODE. And again, this is going to work on I, where I is the common interval of definition for the general one and the particular one. And that's the theorem. That's what we need to do. Now, there is a problem here. Why do we have a problem? Well, as I said, there's two things we need to do. We need to find the general solution for the homogeneous case. We know how to do that easily. However, we don't have an algorithm for finding y sub p, a particular solution to the non-homogeneous case. So that is the problem. However, if we find a way to find y sub p, the particular solution, then we're done. We know how to find the general solution for the non-homogeneous case. So that is what we're going to do next. We're going to define an algorithm for finding y sub p, the particular solution or any particular solution to the non-homogeneous case. And again, we only need one, right? So I'm just going to give you an algorithm to finding one such solution. Now, the way of finding y sub p is going to be by this method, which is called the method of undetermined coefficients. Okay. Now, before I go into the method, since it's going to be a little bit long, the first run, because I'm going to be explaining how it works, I'm going to stop here and cover this in the next video. And we're going to basically derive the method by working through an example, as we usually do.